All right. Thank you, Andrew, for that very nice introduction, and thanks for inviting me also. It's my first time in Russia. I'm really excited also about seeing the country here in the weekend. So can you hear me up in the back? I'm yelling enough? No? Yeah? All right. So I should try to keep you awake here in the last couple of hours of the day. I hope it's not going to be too difficult, but I will say, though, that I'm probably going to be slightly, if not a lot more technical than we've been so far. So I'm actually going to try to be fairly low level in the sense that I'm going to look at very simple problems and then actually do them all the way through in this IO model that I'm going to talk about in a second. I also want to say that that I actually think the previous lectures today have actually been a very nice introduction to what I'm going to say. So I actually don't have to say much about this. Actually, I think you've seen all these magazines up here already that basically says lots and lots of data. We generate much more of it than we've ever done. It's going to change the way we think about science, and it's going to change the way we think about business. All right, so that's basically what both Pino and Tony talked about, that big data is out there and it's coming more and more, and there are really some opportunities both in science and in business. So that's basically what I'm going to say about that. One thing that Pino also, maybe I should go back, Pino pointed out this morning, so I don't have to say it much either, is that you can view big data from many different angles, right? Cloud computing, Hadoop, what do I know, data mining. But the view I'll take in the next couple hours, and also on Monday, is the same as Pino took this morning, namely algorithms. So I'm going to look at algorithms for handling big data sets, and not only that, I'm going to look at algorithms for handling big data sets in a very limited model, one machine. All right, I have one machine, but of course, a lot of the stuff I'm saying you can take and use in distributed or parallel settings also, but I'm going to stick to one machine. And then I'm going to start out telling you that we used to program and think about computers like this up here. Even if you don't think you think about computers like this, you actually do. So it has a processor, and then it has an unlimited memory. And in the theory community, or algorithms community, we would call the random access machine. So we can read and write a memory location in one time unit, and we can do an operation in the processor in one time unit, and it all costs the same. But the reason why I said that you actually think about the computer like this is if you ever programmed anything, right? You think about it like this. You think about having an infinite memory. You just read and write. You allocate when you need memory. And even though this is not true, right? You don't have infinite memory, and there's all kinds of other issues going on in the machine. The operating system and your programming environment make you think that the computer looks like this. And actually, some people argue that this is actually some of the main reason for the early success. I think there's other success going to come soon, but the early success of computers is this very clean and simple model of thinking, both in theory and in practice. But of course, it doesn't look like this. It doesn't look like this up there either, but this is what I'm going to talk about. So a machine doesn't have infinite memory, right? It has a whole hierarchy of memory, registers, caches, maybe more caches, a limited main memory, a disk, a network, other machines' memory, what do I know, right? So there's a hierarchy of memory, and that holds true for everything you can think of. It holds true for this thing and this thing here and the thing on your desktop and other things. They have a hierarchy of memory. And the further you get away from the processor, the slower the memory becomes. Okay? And also, data, when you want to use data, you got to bring it into the processor. So if there's data sitting out on disk, you got to bring it in all the way through the caches to actually operate on it. And the way you bring it in is by moving it between levels. And when you move it between levels, you move it in big blocks. So blocks of data. You just don't get one piece of data. You get a whole block of it. And, whoops. I thought I had another one there. I didn't. Okay. What I'm going to especially look at is, interesting, this level out here, the disk. The disk is a mechanical device. When you want to read something on a disk, let's say a piece of data here, You got to wait till this spinning platter comes around. You got to move a read-write arm to get to the right piece of data before you can read it. And that actually means that this disk is really, really, really slow. It's actually 1 million times slower than main memory. All right, so if you have data in main memory and you're working on it, it's fast. If it sits out on a disk, if you're unlucky that the piece of data you want to have working on it sitting out on a disk, it takes 1 million times longer suddenly. My favorite quote, the difference between CPU speed and disk speed is the same as if you want to sharpen a pencil. I guess nobody sharpens pencil anymore. But if you want to sharpen a pencil, you can either do it here, or you could travel to Australia and do it. It takes 1 million times longer. Okay, so now this is also the reason why data is moved in big blocks, right? Because if you've been sitting there waiting for the platter to spin around and the arm to move to the right spot to get one little piece of data, you can get a lot of data around that place, right? For almost free, because you spend so much time getting there. So why not move some more data into the machine while you're there, hoping that you are actually using it? So that's the reason why you move things in block, and that's the reason why it's important to compute in a way where you have locality, meaning if you touch a piece of data here, you should touch the piece of data next to it in a minute, and next to it again, right? So you should have locality in your access to data. You shouldn't be jumping around, because if you're jumping around, then they also have to be jumping around on this very slow disk and bringing in big chunks of data that you're not using for anything. And already here, I hope you can feel why I said that even though I'm going to focus on one machine with one disk, I am going to talk about how to get locality in computations, which also is one of the things you want in a distributed or a parallel environment, right? So you can use some of the techniques I'm going to talk about in those settings also. Now, as I said, most programs, when you program, you don't really care about what I just talked about, moving big data around and where it sits in memory. You just assume that it's there somewhere. You can allocate big arrays or whatever you want. So there's an operating system that works underneath you, taking care of moving things in and out. And the operating system is, of course, also trying to get the right data, predicting what data you're going to use in a minute so that it's there already, trying to hide this very slow disk. But actually, if you are jumping around in your data, the operating system have no chance of helping you, right? So if you design an algorithm that jumps around, it's going to take you a lot of accesses to the disk. And then you get performance like this. If you have data size and running time, it goes nicely up as the data size goes up. The running time, of course, goes up. But then at some point, it jumps. It jumps a factor of 1 million. Right? It jumps exactly from the time where things can sit in the machine until it cannot sit in the machine. Then everything gets 1 million times slower if you have to get out on the disk every time you touch something. So that's what we want to do something about. Now, I wanted to point out here that, of course, I drew this picture, so I could do whatever I wanted, but I drew small jumps here also, right? Those correspond to jumps in the other levels of the memory hierarchy, because we actually have the same issue between cache and main memory, and between caches, that suddenly things get more expensive as the data set gets bigger. So you have the same effects on many levels of the hierarchy. And if I have time, I'll get back to that in a minute. All right, so motivated by this is what I'm going to talk about. External memory algorithms, or I/O algorithms. I'm going to use both terms. So I'm going to look at the machine as this. I have a disk, and I have a main memory and a processor. The main memory have limited size. It can hold m elements. Okay, whatever elements you're working on, the main memory can hold m of them, and the disk can hold an infinite amount of elements. I think I want to go over here in the shadow. And when you can only compute on things that are sitting in memory, and if you want to compute on something that's sitting on a disk, you got to move it into memory in a block of size b. All right, so every time you go out on the disk and get an element, you get b, and that's one I/O. To make room for it, you might have to actually write something out to the disk, and that you also do in blocks of size b. And the only thing I'm going to care about, because I'm basically a theoretician, right? It's not quite true, but the only thing I'm going to care about here is the number of IOs. So I'm only going to count the number of blocks that I move to solve a problem. Everything I do in here is for free. Computation is for free. It's only movement that counts. In some of my algorithms, I'm going to have an extra parameter t, which is going to be the number of items or elements in my output, but we'll get back to that a little later. I'm going to assume, but only for convenience, I could remove this assumption, but it's just easy when we do some math later on. I'm going to assume that my main memory holds more than b blocks. Here it says m is bigger than b squared. That means that m over b, which is the number of blocks in main memory, is bigger than b. So the number of blocks that I can hold in main memory is bigger than b. Okay, are we with me so far? Feel free to ask questions, right? Even if it's late. Yeah, good. Yep. 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 And also write. Right? So every time I write B elements or read B elements, it costs me 1. This is only because it makes some math easier. Yeah, but it doesn't, I mean, I don't need this. I don't need this. Actually, the only thing I really need is that m is bigger than 2b, right? It doesn't make any sense if I can't hold 2 blocks in memory. But I'm actually saying here that I can hold b blocks in memory. But it's only because it makes life easier for me. All right, good. Feel free to ask questions, right? Because it's late in the day and all this stuff. All right, so this slide I'm going to spend some time on, because here I'm basically going to tell you everything that you need to know. Then I'm going to tell it again to you during 4 hours of lecture. But here's what you need to know. Now, if you think about a normal internal memory, you know that you can read n elements in n time, right? That's easy. You can sort in n log n time in a comparison model. I hope you all know that. You can permute n elements. So permuting is, if I give you n elements, right, I give you the numbers from 1 to n, and then I say, move them around so they appear in the order 87, 26, 47, 1, 4. I give you some permutation, right? And you should move them around. You just move them one at a time, right? You look at the first element and you say, where did Lars say you should put it? And you put it there. You take the next element and you say, where should I put it? And you put it there. That takes you linear time, right? So permuting also takes linear time, just like scanning. And I hope you also know that searching you can do in log n time, right? So normal search tree and normal sorting. Now, in the external memory model, which I just showed you, this model here, right, where I count IOs and blocks, things looks a little bit more complicated. But let me try to translate it to you. N over B, here scanning, just reading an input of n elements, normally takes n time. Here it takes n over B. N over B is really what is linear, right? You're used to n being linear time. But n over b is linear I/O, because since I can read b elements in one I/O, if I need to read n, I need n over b IOs, right? So n over b is actually what I would like. N over b is a really good bound, right? It's the minimum number of IOs that I need just to read n elements. Okay? N over b is our friend. Good. Now sorting looks slightly more complicated. N over b log base m over b. Log, oh, here the base is 2, right? N over b. What does it really say here, right? It looks complicated, but it isn't really, right? Because we just agreed that n over b is linear. So it really says linear log linear, just like it does over here. Linear log linear. Except that the log was 2 here, and here it's m over b. M over b is the number of blocks in main memory. Right? So here it basically says n log n, just with a different base, which is the number of blocks in memory. And you'll see in a minute why. Now, permuting is where it gets really interesting. And which actually I think makes this field interesting. To permute n elements, Normally, I said I can just move them around one by one. I could do that also, right? That would take me n IOs. But actually, the lower bound says that to permute n elements, you need the minimum of n and the sorting bound. Which one is minimum? Well, it depends on B and N and M, right? But typically B is very, very, very big. B is on the order of thousands. M is also big. So M over B is very, very big too, which means that this logarithm here is very, very small. So here let's forget it for a minute. So here it says the minimum of N and N over B, and B is very big. So this term here is always going to be the smallest in practice. Okay? So here it says that permuting and sorting cost you the same. You cannot just move elements around one by one. You can do it much, much faster by sorting. All right? Or put another way, if I tell you to sort and I tell you to permute, they're equally hard, meaning the hard part of sorting is not finding the order. The hard part is actually moving things around. You're used to this n log n here coming from an information theoretical argument, right? The hard part is finding the order. In the I/O world, the hard part is moving them around. That makes life really miserable, or interesting, depending on how you look at it. Yeah. So just imagine I give you a permutation and n elements and say move them around. That's my. Oh yes. So that's actually also, if you look at these bounds here, if n is smaller than m and all this, well, let's assume that n is much, much bigger than m. But these bounds actually becomes these bounds when the parameters get small. Yeah? Let's go through. I'm actually going to show the upper bounds, then you'll see, and actually the lower bound too, then you're going to see it. And searching, I'm not going to talk about so much today, but on Monday, but there's also a difference here in the base of the logarithm. Now let me say that in a second. I want to make this point here. The B factor is very, very important, right? N over B is smaller than this sorting factor, but this log is very small. And it's very, very much smaller than n in practice, right? So going from an algorithm that uses n IOs to one that uses the sorting bound IOs really means a lot, okay? And also a thing I want to say that I'm not going to touch so much on today, but on Monday I will. You're used to being able to sort using a search tree, right? If you want to sort n elements, you insert them all in a search tree and you take them out again. It costs you n log n. If I do that in external memory, I get n times log base b of n. That's really, really bad, right? Because I need a b there in front, and I need the logarithm to be much bigger than m over b. So you cannot sort efficiently using a data structure. That's a lie, but for now it is not a lie. All right, so you get this? Well, I'm going to go through it again. Oh, I don't have to go over there. I just want to drive home the point that this is important. Pino talked a lot about graph algorithms this morning. Here's the simplest graph algorithm you can think of. The simplest. Traversing a linked list. All right? Sometimes we call it list ranking, meaning I'm going to number the elements in a linked list. Okay? So let's say that I have a linked list here. So 1 points, 1, 2, 3, 4, and so they point to each other, right? I've stored a linked list in an array. And I'm on a very small computer. My disk has a block size of 2, and my main memory can hold 4 elements, 2 blocks. Okay? Small linked list, small machine. Now I start running an algorithm on this array over here. I want to visit them all in order, just running through the list. I load 1. When I load 1, I get 5 for free, right? Because my block size is 2. So I get 5 for free. Then I need to follow the pointer to 2, so I load 2. I get 6 for free. Now my memory holds 1, 5, 2, and 6, and it's full, right? because it can only hold 4 elements. Now I need to follow the pointer from 2 to 3, but before I do that, I need to kick something out of the memory, because I want to load 3 and 8. What do I kick out? Least recently used, right? And that was the first block. So I kick out 1 and 5, and I pull in 3 and 8. Now I've visited 1, 2, and 3, and I've done 3 IOs. Right? Now I pull in 4 and 9, kicking out 2 and 5. Visited 4 elements, done 4 IOs, and of course I cooked the example, so this continues. Right? Now I load 5, and I get 1 for free. I can use 1 for absolutely nothing, because I used it already, right? Then I load 6, I get 2 for free. I can use 2 for absolutely nothing, because even though it was there already. So I'm really wasting IO here, and I end up spending 10 IOs. Okay? On the other hand, if my data has been stored differently, like this, I'm running the exact same algorithm. I load 1, I get 2 for free. I load 3 and get 4 for free. I load 5 and I get 6 for free, and so on. So if my algorithm does the same, but my data is stored differently, I only do 5 IOs. And this is actually the difference between n and n over b. Okay? Or you're getting tired now because you think, why is he doing this? I'm doing this to explain to you that this matters. Because if I put in some numbers here, 256 meg data, 8,000 block size, and millisecond disk, this algorithm here uses 71 hours. This one uses 32 seconds. It really matters. All right? So the difference between n and n over b really matters. So let's design some algorithms. Here's what I'm going to do today. I'm going to show you how to sort. I'm going to show you the permuting lower bound. If I have time, we'll see how that goes. I'll talk about cache oblivious sorting. You don't know what it is, but I'll tell you. And then I'm going to talk about solving some batch geometric problems. So if you have some geometric optims, you want to solve a problem on them, you can use this technique. And this is also where I'm going to ask you a homework. So I hope this motivates you to pay attention along the way here. And then on Monday, I'm going to switch to talk about data structures, searching, batch searching, priority queues, and then list ranking. And list ranking with this problem I just motivated, or showed you why it matters. I'm actually going to show you how to solve the problem. And it's not as simple as it sounds. And that's what I'm going to end with. All right? Questions so far? No? Good. So I want to sort. But before I want to sort, I want to do something even simpler, just to warm up here. I want to implement a queue. How do you implement a queue in external memory? Well, so a queue, of course, is something where you can push in one end and pop in the other end, right? How do you do that? Well, you keep 2 blocks in main memory at all times. And when you want to pop an element, you just get it in the block that's sitting in memory. So it costs you nothing. It's free. The next one is also free. The next one is also free. You can keep on answering pop operations for free until your block runs empty. What do you do then? Well, then you load a new block. Similarly, if you want to push, you can push for free until the block is full, and then you write it to disk and make a new block in main memory. The only point here is that push and pop operations cost you 1 over b amortized, 1 over b on the average, right? Many push and pops are free, but once in a while it costs you an IO. On the average, it costs you 1 over b IOs. Sounds trivial, but we're going to use this a lot. The same thing holds with a stack. I just keep blocks at the end here. Next primitive that I'm going to need for sorting uses this pushing and popping. So one very key primitive in external memory algorithms is that I can merge m over b sorted lists in a linear number of IOs. Okay? So here, imagine that you have m over b minus 1 sorted lists. So the arrow here means that they're sorted. And I want to produce an output which is the merge of these lists, right? So the sorted lists consisting of all these merged together to one sorted list. That I can easily do in 1 over b IOs. Why can I do that? Well, I just use a stack here, so I pop elements from each of these, and then I pop one element for each of these, and then I push the minimum. And I keep doing this. That every time I touch an element, every time I pop something over here, it costs me 1 over b. Every time I push something over here, it costs me 1 over b. So doing this to n elements costs me n over b IOs. Okay? What's really going on here is that I load one block for this input, one block for this input, one block for this input, and so on. I spend m over b minus 1 blocks to hold a block for each of these. And then I hold a block for the output. So I look for the minimum among these, put it here. Look for the minimum among these, put it here. Look for the minimum among these, put it here. If either this one runs full, I push it out, or if one of these runs empty, I pull in the next. Okay? But the key here is that I can do this m over b wise merging in linear I/O. You're used to doing two-way merge in linear time, right? You can merge two sorted lists into one sorted list in linear time. I can actually do better in the I/O model. I can merge m over b lists into one list in linear I/O. Okay? I can also do the opposite. Here I just turn the picture upside down. I can take one list, and if I know some split elements between them, saying, here I should put all elements between 1 and 27, here I should put all elements between 28 and 48, and so on, then I can also do that in linear I/O. Okay? With this primitive, I can easily sort. Here's the first sorting algorithm, merge sort. How do we merge sort? Well, we start with our elements here we want to sort. We break them up. We read them m element at a time. I take m elements, bring them into memory, sort them, and put them back out. The next m elements into memory, sort them, put them back out. That gives me these guys here, n over m lists that are all sorted, right? And now I start merging them together m over b at a time, using this primitive up here, right? Okay, so let's see. Here I have one list. On this level, I have n over m lists. Here, after merging them together, m over b at a time, I have this many lists. I merge them again, until I get down to one sorted list. How many levels do I have here? Well, log base m over b to the number of lists I started with. Aha, this was where this weird log came in. Think about if you were doing normal merge sort, you would merge things together 2 at a time, right? So the height of your merge here would be log n. Here I merge things together many more at a time, so my height of my merge is smaller. And the height of it is log base m over b to the number of things I started with. Now in each level here, I actually will argue that I only spent linear I/O. Right, from taking this list and producing these sorted things, I just read all the elements once and I write them once, right? Merging these guys together to this guy, I spend time linear in the number here. Using these merged to these, I spend linear, and so on. So getting from here to here cost me linear. Getting from here to here cost me linear, so on. So on any level, it costs me n over b IOs. I have this many phases, so I spend this many IOs in total, which was exactly the bound that I told you I would show you. Okay? So now you know how to sort optimally, namely using merge sort like you're used to, except that instead of merging things together 2 at a time, you merge things together m over b at a time. Yeah, yeah. Yeah, yeah. Mm-hmm. Nicely spotted, nicely spotted. Good. So he says, how did that m here become this b? Right? That's what he's saying. Any answers? Yeah? Yes, it doesn't matter because of the base of the logarithm. Good. Excellent. You're still awake. It's really good. Keep them coming. All right, so that was merge sort. I can do the opposite also, right? Just like I, on this here said I can turn the whole process upside down, I can also turn this upside down. And then I get distribution sort or multi-way quicksort, right? So I take my elements and I compute M over B splitting elements. So I compute these elements. Remember when I said over here, to take this and distribute them, I need to know how these buckets are defined here. So if I can compute these split elements, then I can take my input, divide it into M over B buckets, divide each of them into M over B buckets, divide those into M over B buckets, until I get buckets of size M, which I then sort in memory and put them back out, right? So it's the exact opposite of what I did before. Each of these levels I can do in linear I/O. So, and the height of this is this famous logarithm here. So if I can compute these elements that split the data in linear I/O, then I'm good. I hope you know that this corresponds to deterministic quicksort, right? If I want a quicksort, I want to find the middle element. I can find the middle element at linear time. It's difficult, but I can do it. The question is, can I find M over B elements that splits the data up into nice chunks in linear I/O? And the answer is yes and no. The answer is I can if I don't demand that I need M over B, but only root M over B. So what I'm really saying here is that the fan out here is not M over B, it's root M over B. I won't go through it because that's going to take me too long. It's not that difficult, it's just hairy. But luckily it doesn't mean anything because log root M over B to this is the same as log M over B, right? The difference is only a factor of 2 if you do the math. So it doesn't really matter if I'm merging M over B, distributing M over B things or root M over B, I get the same asymptotic bound. Okay, so distribution sorting, multi-way quicksort also works. If you think quicksort, you could also just choose these M over B elements randomly, right? Then it would be quicksort. Okay, so I can now have 2 sorting algorithms, merging or distributing, but the only thing they both use is this M over B wise merging or splitting. Okay, now we got that was an upper bound. There were 2 upper bounds, algorithms. Now I'm going to do a lower bound, which is always a little hairier, right? But I thought I wanted to put this in to give you a flavor of why it is we get these weird bounds, right? Because I'm going to actually show you the permuting bound. So I'm going to show you that to permute elements, n elements, so this thing about moving them around, basically requires me to sort, which is weird, right? I hope you think it's weird. But it is weird, right, that I can't just move them around. I actually have to sort. And I'm going to show you why that is the case, because that's sort of a key thing in the I/O model. And I can reveal to you also that this actually means that you get the same bound for all kinds of graph algorithms like Pino was talking about, right? If I can't permute things, I can't run through a linked list in linear time, then I can't do any graph algorithm in linear time. Linear I/O. So I'm going to show you to move n elements around according to a permutation you give me. In the worst case, I'm going to have to use this many I/Os, which is in practice is the sorting bound. Now I'm going to prove it in the indivisibility model. For purposes of this proof, the indivisibility model is going to be I'm only allowed to move elements. Okay, I'm not allowed to make new elements, I'm not allowed to delete elements, I'm not allowed to do arithmetic operations on them, I'm not allowed to do anything. I can only move them around. Okay? Actually, in this model, I can actually allow for making copies and also deleting elements, and I'm going to tell you in a minute why that's the case. But think about it now as if I'm only allowed to move elements around. Another thing is that I want to say is that if this is a lower bound for permuting, then it's also a lower bound for sorting, right? If I take this many IOs to move n elements around where I know where they're going, then I also need this many if I don't know where they're going, right? In sorting, I don't know where the elements are going. So that's a harder problem than permuting. So this lower bound is also a lower bound for sorting. All right, here's the proof in, I guess, 2 slides. All right, so I'm going to view my main memory and disk as one big array. I drew down here so that you can visualize it. I don't know why it's jumping such up and down. Maybe I had too much vodka. So I have my main memory sitting here and my disk sitting here, and I view it as one big array. And I also imagine that I've divided the whole thing up into chunks of B, and I call them tracks. Right? So these are the things I've drawn here. So there's a bunch of tracks here. Some of them are memory and some of them are disk. In fact, I'm going to assume that there's only n of them, because I only have n elements. So there can only be n blocks that actually contain anything, right? So I have n tracks here, some of them in memory, some of them in disk. And I can only move stuff around. I'm also assuming that when I do an I/O, I move one of these blocks in or move one of these blocks out. I can actually relax that assumption a little bit, but that I can read across boundaries, because I can simulate an I/O across a boundary with 2 I/Os that are not crossing a boundary. All right, so I hope you can remember this model. Otherwise, I have at least the array down here to remind you. So here's going to be my proof. If you look at this array and these n elements that are sitting there, in the beginning, they probably sit here, right? At first on the disk in n over b blocks. At the end, they also sit here at the beginning of this in n over b. But along the way, some of them are sitting here, some of them are sitting here. But if you look at them and you remove all the space, right? So imagine that your elements are spread out here. You just sort of squeeze the whole thing, right? Then at any given time, you have n elements sitting in a linear order in the array, right? And it's a permutation of the original n elements, right? So whatever I do, I move stuff in and out. At any given time, I have a permutation. I start with a permutation, I end with a permutation, the one I want. And along the way, I have a permutation. So at any given time, I have a permutation. That's basically why I define the model like this. That's why I don't want copies and all this stuff. I have one permutation at any given time. What I'll do in my proof here, I'll count how many permutations that I can actually produce. All right, when I haven't done any IOs whatsoever, how many permutations can I produce? 1, right? The one I have, right? Right? If I haven't done any IOs, my input is the permutation. I can only produce 1 IO output. That's the permutation. How many permutations do I need to be able to produce? N factorial, right? There's n factorial different permutations. If I can't produce them all, you will ask me to produce that permutation that I can't produce, right? So I have to be able to produce them all. Okay? Now I'm going to count how many new permutations that I haven't produced before can I produce every time I do an input and output, right? Then I'm going to compare that to n factorial, and that I'm going to get a lower bound. And input. When I do an input, I produce some number of permutation, initially 1. Now I do 1 input. How many new permutations can I produce? Well, that relates to how many different choices I can make in where I take elements and where I put elements. I can choose n different places to take my elements, to take a track, right? To load a block. For every one I choose, I might get new permutations, right? If I take this guy and move them in here, I get a new permutation. If I take another guy here and move them over here, I get another permutation, and so on. So that gives me n possibilities, because there are at most n tracks. There's actually less, but let's say that most n tracks where I can choose a permutation. So I take a track here, I put them in here. Once I've done that, I can also move things around in here, right? Actually, I can arrange these B up to B elements that I just got in. I can move and put them among the M minus B elements that I have already. right? I have m over b, m minus b elements sitting in memory. B elements comes in, I can put them in different ways in here and create different permutations. How many different ways can I do that? Well, at most, b factorial m choose b. It's actually less than that, but this is definitely an upper bound. Right? B factorial is taking these b elements I got in, moving them around among themselves, right? And then m choose b is the one number of ways I can put b elements among m elements. So this is it's an upper bound on the number of permutations that I can produce when I take and put them in here. Except that's a lie. Because it only is true when I get a fresh track, ones that haven't been brought in before. Because if I already had it in and put it out, then I've already permuted them among themselves, right? So bringing them in and permuting them among themselves doesn't give me anything new because I could already have done it. So it's only if it's a fresh track that I get the b factorial term, otherwise I only get m choose b. Okay, so that means that after t inputs, I have at most produced b factorial to the n over b. That's the number of blocks that I had elements in to begin with. That's the number of fresh tracks. And then n times m choose b to the t. N ways of choosing the track. M choose b to put them among themselves in main memory. I can do that t times. So now I've bounded the number of permutations I can do after having done t inputs. Yes? It's because any input consists of n elements sitting in n over b blocks. So there's only n over b times that I can take in a track that I've never seen before. Good? Other questions? Good. Now comes the kicker. What about an output? Well, I can take stuff in here and I can put them in n different places. And that's actually the only possibility I have, right? I cannot count moving them around in here already because I've already counted that. So I can just take a block and put it out here. There's n possibilities for that. But I can upper bound that by the same amount here, right? So I do that. So in other words, I just have to solve this equation to get a lower bound on t. This is the absolute maximum number of permutations I can produce with t input outputs. It's actually an overestimation. I need to be able to produce n factorial. Right? Okay. Okay, so here I just do some math. I cheat, so hand wave a little bit. Stirling's formula tells me that log to x factorial is x log x. So that's, I've taken log on both sides. And then I use this formula, and I also use, if you do the math, you see that you can also do this. So I get this. Then I get this. All right, so here it says t is bigger than this n log n over b over log n plus b log m over b. That's not very nice to look at, so let us look at the case where log n is smaller than b log base m over b, log m over b, sorry. Right, if this is the case, then this thing here goes away, or rather I can replace it with the 2. So it says t is bigger than this divided by this, which is exactly my sorting bound. Okay? So if this guy dominates here, down here, then it becomes the sorting bound. Let's see the other way around. If log n is bigger than b log m over b, well, if log n is bigger than b log something, then log n is bigger than b for sure. And if log n is bigger than b, then b is root n is also bigger than b, right? So if this is the case, then this is also the case. And now I can start putting in things. Up here I get this, because this one goes away now and becomes a 2. And if you do the math, you get that it's at least half n. All right, so that proves my lower bound. Either this is when this is a lower bound or this is a lower bound, then the minimum of the 2 is a lower bound, which was what I promised to prove to you. All right, so permuting elements requires you to either move them one at a time, costing you NIOs, or sorting them, costing you this sorting bound IOs. On a normal practical circumstances, this is going to be the optimal because it's smaller than n. And the argument I used to prove it to you was just a counting argument that counted how many permutations can I do after TIOs and comparing that to n factorial. So as I said on the, no, maybe I should actually say, I'll give you a break in 2 minutes, so don't worry. But I said over here that when I started out, I said that I would assume that I cannot make new elements or destroy elements, but actually I can allow copies and destruction of elements, as long as the n elements that I end with are the same as the ones that I started with, right? Why is that the case? Well, if you think about the way I did the lower bound here, what I counted was number of permutations I can reach. That actually means that there is one hard permutation out there, right? Since doing a permutation would cost me this many IOs, there must be one that costs me this many IOs, right? So whatever algorithm you make, it has to be able to handle that one permutation. If your algorithm produces new elements, copies of elements, and deletes them again, and produces a sequence of IOs that takes me from the original elements to a permutation of the original elements, whatever you do in there with other elements doesn't matter. My lower bound still holds, right? Because I can backtrack from your end permutation to your input and make a sequence of IOs that solve the problem. So that assumption I don't need, actually. I just want to end by saying that I can prove the sorting lower. I claimed to you that the sorting lower bound was the same, except it didn't have the minimum of n and sorting. It only had the sorting. That is true, but I have to assume the comparison model in internal memory. So I have to assume, just like in the permuting case, I assumed the indivisibility model that I can only move elements. If I want to prove something for sorting, something else for sorting, I assume that I can only compare elements in internal memory. And then I do exactly the same. I said that when you give me n elements and tell me to sort them, then there could be n factorial ways that were actually the right output, right? And every time I do an input and output, I can look and compare elements. That brings down the number of sortings that could be the right one, right? So I do a counting argument where I count after TIOs, how many sorting could still be the right one, and I want to get that down to 1. And when I do that counting argument, I get the same formula as I did before, except I don't get this n here. Intuitively, I can also explain to you why I don't get this n. Remember, this n I got from where I could choose which track I wanted to bring in. When I choose which track to bring in, I haven't learned anything about my input, right? I learned something about my input when I compare things. And that's actually going to give you the other bounds. And if you then do the math without this term, you don't get this term, and then you get the sorting bound. Okay, so here's a summary of the first hour here. I've told you that you can do, or summary of sorting, you can do merging and distribution sort in this bound. The key to doing this is doing M-way merging and distributing, except that in the distributing phase, you only do it root MOB way instead of MOB way. I told you just now that it's optimal in comparison model, and it's almost optimal in this indivisibility model, where the bound also holds for permuting, and I showed you that. Okay, so now you know everything there is to know about permuting and sorting. And I think we have a question. Did we? Or no? Back? One more? Or? I didn't tell you how I got this. I didn't tell you how to get this. I mean, I told you how to get it over here, right? In the permuting thing. Oh, you want to know it in the permuting bound? Oh, yeah, so here I got it because when you bring in B elements, right? You bring in B elements, I can move them around them among themselves. The number of ways I can do that is B factorial. It's bounded by B factorial. And then afterwards, I can place them among the ones I have already. And the one I have already is M. It's actually M minus B. But I'm upper bounding, so it's fine. Okay? Good. This is what I did so far, right? I talked about upper bounds for sorting, merging, and distribution sort. Then I gave you the lower bound. And actually, I'm doing so good on time. So I will actually do now cache oblivious sorting and then the best geometry. So you didn't ask enough questions, right? I'm on time. So you got to do something about that. But let me just show you this again, so to get you back in the mood if you're not. So we saw how to do merge sort and distribution sort, which is basically this picture, one way or the other. But the key is that we can merge M over B things or distribute M over B things in linear I/O. So the number of levels here is this log, and on each level I use linear I/O. And the lower bounds are then counting lower bound. The one I showed you was counting permutations, but I could also be counting possible sorting solutions. I also heard in the break that some people have actually had a class on this before, which just makes it better, right? So, because you can ask all the intelligent questions and all the mistakes I make, so that's your task. All right? Okay, so now let me talk a little bit about cache oblivious sorting, which is something I put in actually here earlier today in one of the breaks because somebody was telling me that I should really say something about cache oblivious. So I will say something about cache oblivious. Since I'm doing sorting here, I'll talk about cache oblivious sorting. So let me first tell you what the cache oblivious model is. So the cache oblivious model is basically the same as I've been talking about so far. I look at the machine as this. And I also have the parameters n, b, and m, and I also assume that m is bigger than b squared, except now it's actually important for some of the things I'm saying. Now I have to require it. It's called the tall cache or something. But it's all the same that I've been doing so far. What's different is that I'm not allowed to use m and b when I describe an algorithm. Okay? That means that I cannot do the two sorting algorithms that I just talked to you about, right? Because in those two sorting algorithms, I said, in merge sort, I said, bring m elements into memory and sort. I cannot say that because I'm not allowed to use m in my algorithm. And then I said, merge m over b things together. I'm not allowed to do that because I'm not allowed to use m over b in my algorithm. Okay, so those algorithms are not cache oblivious because the algorithm use the parameters of the model. I'm not allowed to do that. That also means that this whole idea of moving blocks in and out is kind of strange, right? Because I don't know how big I cannot talk about blocks in main memory. So I have to assume that somebody else is moving things around. And I'm assuming that I have the operating system underneath me is doing things the best that can possibly be done. I have an optimal paging strategy. Somebody underneath me do the actual movement, and they do the best they can. The good thing about this model, it sounds weird, right? I'm designing algorithms in a model where I'm not allowed to use the model. That sounds weird, right? Sounds pretty stupid. But actually, what I am allowed to use is that I'm allowed to analyze algorithms exactly as I just did in the last hour. So I can analyze algorithms using M, B, and N. Just like I analyze them just like IO algorithms, I'm just not allowed to make them like IO algorithms. That's why we call them cache oblivious, right? They don't know, the algorithm doesn't know anything about the cache or the main memory and disk, but I analyze it as if it's an IO algorithm. The cool thing about it is that if you think about it, if I analyze a cache oblivious algorithm, meaning with M and B, and show that it's optimal, for instance, that it gets this sorting bound that we just talked about, then it's actually optimal on all levels of a hierarchy, right? Because I can plug in any value for M and B. And it'll say, if I plug in the value for M and B here, it'll say, oh, it's optimal here. If I plug them in here, it'll say, oh, it's optimal here. And I can do that on any level. So if I can analyze a cache-oblivious algorithm and show that it's optimal, then it's optimal on all, or efficient, then it's efficient or optimal on all levels at the same time. Not only that, it's optimal and efficient on all possible architectures you can ever think of, right? That has that hierarchy. So it's pretty cool. Under some assumptions, of course, that I won't get into here, but they're actually not very mild assumptions. The question is, of course, if it can be done at all. Can I design a sorting algorithm where I'm not allowed to use M and B? Meaning, can I design an IO-efficient algorithm without M and B and show that it's optimal with M and B? And I hope to show you in the next 3 slides that I can. With a little cheating, but not too much. So this is just another picture of distribution sort, right? In distribution sort, I take my n elements, I divided it into root MOB buckets that I then divided into root MOB buckets again, meaning, and so on, right? What I'm going to do in cache-oblivious distribution sort, I can't divide into M over B things, right? Because I don't know what M over B is. So instead, I'm going to divide into root n buckets of size root n. Okay, I'm going to take my elements, I'm going to divide them into root n buckets so that these elements here are smaller than these, they're smaller than these, they're smaller than these, and so on. They're not sorted individually, but everything in here is smaller than everything in here. And then I'm going to recurse, right? So then I'm going to sort these until I end up with 1 element in each bucket, and they're going to be sorted. It's just quicksort, multi-way quicksort, where the distribution factor is now root n instead of 2 or M over B. Are you with me so far? Because otherwise everything else is going to just go over your head. Right? Got it. Good. Distribution, but with distribution root n. Root n. Okay. Actually, that's not what I'm going to do. You saw the slight change in figure up front, up there. What I'm going to do is that I'm going to take my n elements, then I'm going to sort them root n at a time. So I'm going to take root n here, sort them, 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 and then I'm going to distribute them, and then I'm going to sort recursively. That sounds weird, right? Now I'm going to sort to sort. But nevertheless, that's what I'm going to do. And I'm going to show you that if I can distribute these n elements in root n buckets of root n chunks, sorted chunks of root n elements each into these buckets here in linear I/O, then I'm good. And you have to do some math afterwards to believe me, but here it is. If you think about the recursion for this algorithm, what does this algorithm do? It takes root n chunks of root n elements and it sorts each of them. Then it distributes, and then it sorts each chunk of root n elements, and there's root n of them. That actually means that I have sorted 2 root n chunks of size root n, right? I start up here, I have root n chunks of size root n, I sort them, then I distribute, and then I again sort root n chunks of size root n. That means I've sorted 2 root n chunks of size root n, and then I claim for now, I'm going to show you in a minute, that I can get from here to here in linear I/O. Okay? So twice I sort root n chunks of size root n, and then I do one distribution step using N over B I/Os. If you solve this recursion, you get the sorting bound by magic. The magic comes because I have this condition here that says when I get down to less than n m elements, I only do n m over b IOs, right? Because there's an optimal paging strategy. When it sees, oh, there's m elements, it just loads them in, and whatever you do from there on is going to be free. So solve this recursion, and you get the sorting bound. Yes? I don't know, but it doesn't matter. I know it when I do my analysis, right? My algorithm doesn't know it. But since this is a recursive algorithm, the problem is going to be smaller and smaller and smaller and smaller, right? Eventually, it's going to fit in memory, right? whatever happens, once it's loaded into memory, it's going to stay in memory. Therefore, if n is bigger than smaller than m, it's going to cost me nothing. Good question. Yeah. So if you believe me that this recursion solves to this, then I need some water. Then all I need to now show you is how to get from this up here to this down here in linear I/O without knowing M and B. So that's the same problem here. I have root n chunks of size root n. They're sorted. I want to distribute them according to some splitting elements, and this is where I'm cheating. I'm assuming that I have these splitting elements. It's not hard, but it just makes it easier right now. I want to take these root n chunks of size root n, sort it, distribute them in so that all these are smaller than all these and smaller than all these and so on, but not sorted. Okay? Problem is clear? All right, here it comes. I'm going to divide these up into 2 halves. And I'm going to divide these up into 2 halves. Okay? So I say, okay, I have root n chunks of size root n. Let me look at half of them first, and then half of them afterwards. I also have root n buckets down here, and I also split them up into 2 halves. And then my algorithm works as follows. I'm going to recursively do the following. First, I distribute elements from up here down to these here. Could be this. Some elements from this guy goes here, some goes here, some go here. Some from this guy go here, some go here, some go here, and some go from here, go here. The rest should go over here, so I don't touch them yet. But recursively, I do this. Right? It's the same problem as the original problem was root n chunks of size root n. This problem here is half root n chunks of size root n into half root n buckets. So it's a recursive problem. Once I've done this, I do this recursive call. I distribute stuff from here down here. It's this line. Then I do this recursive call, this one with this guy, and finally this guy with this guy. So I do 4 recursive calls where I distribute root n chunks of size root n into half root n chunks of size root n into half root n buckets. My original problem was root n chunks of size root n into root n buckets. My recursive calls are half root n chunks of size root n down to half root n buckets. And I do 4 of them. You look very mystified, which is good, because this is exactly what cache oblivious algorithms do to you. You think, what is going on here? Right? You do all this recursive stuff, but it's the only thing you can do, because you're not allowed to use M and B. But what are we really doing? We're trying to make this problem smaller and smaller and smaller in a very controlled way until they fit in memory and then automatically are going to be efficient, right? And then we're doing a complicated analysis to show that it actually works, which is exactly what I'm going to do now on the next slide. I'm going to show you that it works. Look at this. I've tried to draw to you here the recursion tree, right? So I start up here with a problem where I have root n buckets of size root n. I made 4 recursive calls where my buckets was, where my chunks, where I had root n half chunks into root n half buckets. Those each do 4 recursive calls where my things shrink to root n over 4, right? So the number of buckets I have keeps shrinking with a factor of 2. Until eventually I get down to a level where the number of chunks and buckets is b, right? I start with root n half, root n fourth, root n eighth. Eventually it becomes b, right? I don't know what b is, but eventually it becomes b. How many are there of these? So I'm basically asking you, how many things are there on this level? Well, there's 4 to the height of this tree here, which is log root n over b, right? I need to go from root n to b, so the height here is log root n over b, and each time I explode with a factor of 4, so 4 to the log root n over b is the same as n over b squared. So down here on this level, I have n over b squared recursive calls. I start up here with 4 recursive calls, 16 recursive calls, and so on. Eventually, I get down to this level, and I have n over b squared recursive calls. On these recursive calls, I have b chunks of size root n, and I'm distributing them down into b buckets. So I have this. I have b chunks of size root n, and I'm distributing them down into b buckets of size root n. I claim that I can do this. Oh, it's up there already. Whoops. I claim that I can do this in this many IOs. One of these calls here, I can do in b, or the optimal algorithm will automatically do it in b plus the number of elements divided by b IOs. Why is that the case? Well, it's because if you think about distributing these into these, whatever the algorithm does, it can keep a block for each of these buckets down here in memory, right? Right? There's b blocks, and I assume that my memory is bigger than b squared, right? M over b is bigger than b. So one block for each of these buckets here can fit in memory. So whatever my algorithm does, it keeps these first buckets in memory. And then stuff is going on. It's putting stuff in this bucket. When they run full, they output, right? And you take the next bucket. So once I've loaded b blocks, everything else happens blockwise because it's an optimal strategy. So I end up spending b plus number of elements I move over b on each of these thingies down here. Well, that is this many IOs, right? I have this many recursive calls. They each cost b. The rest of it is linear, so it's n over b. So I did all this weird recursive splitting stuff just to make sure that eventually I end up with a problem that looks like this, that magically will happen efficiently. Good. Ooh, that was... Yes? Good question. So you got me, right? I said I assumed up here the buckets is known. What I actually do is that I compute the split elements along the way. Right? I start out, yeah, that's what I want to say. I can say a lot more, but it's going to take me an hour. It's complicated. But it's not something that adds something new. The idea here is to do these recursive calls, right? And that's what if you want to design other cache oblivious algorithms, you do the same flavor kind of thing. The partition thing is just messy, but not really very interesting. So he got me. So anybody else that can get me here? Yeah. Why do I need what? Because why do I need them sorted? That's actually a good question. I didn't say why I need them sorted. I think I actually misspoke down here because you got me. You really got me. No, this is good. This is good. I need them sorted because otherwise I think what I just said down here is not true. Yes, right? Because I assumed, very good question. You get a medal. I assumed that I could hold one block for each of these, and then I would write, no, actually I don't need them to be sorted for that.
Actually, these are on the previous slide.
Do I?
Yeah, when we are distributing into 4.
You're right. There, I love this. Very good. He's right. Otherwise I couldn't do this, right? I couldn't say, let me take the first part here and put down here, because it wouldn't be the first part. It could be intermingled, right? I could not do this and just, here I assume that the first elements that are here goes here, right? And then the rest of them goes over here. That would not be true if they were not sorted. Excellent. Even I get tired at the end of the day. Yeah. Yeah, but I don't actually rely on it very much, right? But you're right. It just keeps these blocks in memory. But it's also the way it actually gets written down into them. So it's not that it's doing something magical. All right, good. So, excellent, I got through this. This was something I plugged in because I thought it would be interesting, and I think it was, because you pointed out that I don't actually remember everything. Now I'm going to switch topic, right? We looked at sorting until now. Now I'm going to, and you sort of have gotten, my goal here, let me just admit that already, my goal is not to show you everything that's known about I/O efficient algorithms. My goal is to show you some key techniques we use along the way, right? And this that's why I keep saying this MOOB, merging and distributing, because that's something we do all the time. Now you've seen this cache oblivious stuff when we do these recursive root n things. That's something we do all the time there. Now I'm going to show you what kind of general idea we usually use to solve geometric problems, batch geometric problems. I don't know why I can't talk anymore. So I'm going to do this by example. I'm going to show you how to solve the orthogonal line segment intersection problem. So I'm going to, here's the problem. I have some red segments, vertical segments, or horizontal segments, and some blue vertical segments, and I want to find all their intersections. Can you see that they're blue and red, or is it just me that can see that? But all the horizontal ones are red, and all the vertical ones are blue. And the reds don't intersect each other, and the blue doesn't intersect each other, but the two sets intersect each other. And I want to find all the intersections. Okay? I bet many of you, well, I don't know actually. Many of you would know how to solve this problem, right? Using plane sweeping. Yeah? Is that true? Yeah? But let's see how we do this. We imagine that we sweep a line across the segments, right? And along the way, we do what it says down here. When we meet the top portion of a vertical segment, we insert it in a search tree according to its x coordinate. When we meet the bottom point, we pull it out again. Okay? That means, if you could see the colors, which I'm sure you can't, that means when I'm sitting here, the segments that are sitting in my search tree is this one, right? Because it's been inserted up here, but it hasn't been pulled out yet. This one has been inserted, but not out. This one is just about to get out. This one, this one, this one, this one, this one, these three there. Those are sitting in the sorted order in the search tree, right? Now, when I meet this segment here, I want to find these intersections. How do I find these intersections? I just ask a range query in the search tree, right? I say, give me everybody from here to here, and it's going to give me exactly these segments there. So it's going to give me exactly the segments intersecting this red segment here. And that's it. This takes me n log n plus t, where t is the number of intersections, time. Why? Because I insert every segment once, I delete every segment once, that's n log n. I ask n queries, that costs me n log n, plus the output size t. With me? Yeah? Yeah? Let's do that I/O efficiently. That's not going to work, my claim. Why is it not going to work? Because I'm using a data structure, right? So I'm saying that I'm maintaining a search tree. I'm sweeping down. Every time I meet a segment, I either insert it in a search tree, or I delete it from a search tree if I meet a bottom endpoint, or I do a query. Every time I do that, I have to visit a search tree structure. That search tree structure could be so big that it sits out on a disk, right? That means that every time I touch a segment, I do an I/O. Since there's n segments, I'm going to end up spending more than n I/Os. N I/Os is bad, right? N over B I/Os is good. That was the first thing we learned. So I cannot have a data structure, using a data structure to do the sweep, because every time I touch this data structure, it might cost me an I/O. And since I touched the data structure more than n times, I'm gonna die. Okay? Yeah? The solution is what I'm going to tell you about distribution sweeping. So distribution sweeping is a general technique, and it is exactly what it sounds like. It's a merge of distributing and sweeping. All right, so we've learned distribution and we just saw sweeping. So now we're going to merge the two, and we're actually going to get an optimal algorithm. So here's how I'm going to solve the problem with distribution sweeping. I'm first going to pretend that I'm doing distribution. So I'm going to take my scene here and I'm going to break it up into m over b, let's minus 1, but let's just say m over b slabs, right? So here's a slab, here's a slab, here's a slab, and so on. There's n over b of these slabs, where there's approximately the same number of endpoints in each. Then I'm going to do a sweep, where I find all intersections involving vertical segments in a slab and horizontal segments that cross a slab. And they should be green up here. Can you see, can people, no? Like there's a green portion here, right? A green portion here, green portion here. So parts of the red ones are becoming green, namely the parts that completely span slabs. I'm going to find in one sweep all intersections that involve a blue segment and a green segment. When I've done that, I can remove the green stuff, right? And then I get this, right? So I remove the green stuff. If I've found all intersections that involve green stuff, then I can remove the green stuff. And then I can recursively solve the problem in each of these slabs, because now they have nothing to do with each other, right? Up here I have a completely separate problem from this problem and this problem and so on. Okay, so basically my algorithm is start with your segments, break them up into these MOB slabs, find intersections that involve stuff that span slabs, and recurse. Okay, so it's sort of distribution by the fact that I distribute and recurse, and it's sweep because I find stuff that involves things in different slabs using a sweep. I haven't shown you how to do this yet, but I will now. Here's how I do the sweep. I've removed everything that's not relevant here. So I'm going to solve this problem, right? I've only drawn the green stuff and the blue stuff. And my goal here is to find all intersections between green and blue stuff. If I can do that in linear I/O plus output, then I actually get this sorting bound plus the output over B. Why? Because of distribution sort, right? It's the exact same thing as distribution sort. With a little cheating. Where's the cheating? It actually does, when I look at this problem here, it looks like things explode, right? Because you see this segment here, right? Part of it goes down into this recursive call. And part of it goes into this recursive call. So it sounds like one element can become 2, which also means it can become 4, which means that things die. But it's not the case. Why not? Because if you look like this, you come in from one side, you're always going to look like that further down, right? Because you're going to get chucked up and look like this in one recursive call. So you only go into 2 recursive calls once. And from there on, you never go further. So I need to show you how to do this sweep to find intersections between the green guys and the blue guys in linear I/O plus some output. And it's a sweep. And I love this. Here it is. It's exactly the same sweep as I did before with a little change. So what I do is that I maintain for each of these slabs, I maintain a list. Remember before in the internal memory algorithm, I had one search tree. Now I have M over B. And it's not a search tree, it's just a list. So for each of these, I maintain a list, and they contain the blue segments that I have met the top endpoint of. Okay, so when I get to this place here, I have this blue guy and this guy and this guy in there, because I've met their top endpoints. But I don't remove them when I meet the bottom. Right, so what's going to happen is, in one slab, I'm just going to put things in a list. not taking anything out. I'm just going to put it in the list. That's push, right? Push on a stack or a queue. We saw that way in the beginning. That cost me 1 over b per element. I'm not taking them out again when I meet the bottom. Why am I not doing that? That would be expensive, right? I can push in stuff at the beginning very cheaply. But if I want to take something out, it could be anywhere in the list, right? That was going to be expensive for me. I don't want to do that. So I just leave them in there. I'm lazy. But that also means that when I then get to a horizontal green guy here, what do? Well, I go to this list, and I look at the blue segments that I have in there. Some of them might intersect me. Some of them might not intersect me, right? I think I might actually have colors, but you can't really see colors. On this slab here, when I get to this piece here, these two guys are still sitting in the list, along with, yeah, these two guys are sitting there. But I don't intersect them, but I go and look at them anyway. But when I look at them, what do? I say, okay, I don't intersect these. There can't be either other people further down intersecting them either, right? So I throw them out. Okay? So what I do is, for these two lists, I run through the lists, and every segment, I either report an intersection and leave it in the list, or I throw it out. So either it's gone, and it's never going to come back, and it only costs me 1 over b, or it stays, but I have an output term to charge it to. Okay? So every element gets put in the list once, it gets pulled out once, that costs me n over b, and then it might actually be read or put in and put out many times, but only t times. So I end up being able to do this, and I'm done. Okay? This is difficult. Let's do it one more time, right? But we'll do another problem. And I promise you, you will do it a third time over the weekend. All right, here's another problem. It looks a lot like the other problem, but it's actually a little harder. Now I have not red and blue. I have just red. I have red rectangles, axis parallel rectangles, and I want to find their intersection. So for every pair of rectangles, you should tell me if they intersect. Or that's not what you should do. You should tell me all pair of rectangles that intersect. I will solve that using distribution tree. So here's the algorithm. I divide the plane up into M over B slabs, containing more or less the same number of endpoints. Then I want to do a sweep where I find all intersections involving rectangles that span slabs. So it's these yellow parts. Once I've found these intersections involving the yellow parts, I remove the, I thought I had an animation that would remove the yellow part. I remove the yellow parts and I recurse. Okay? So I got to show you now how to do this, how to find the intersections between the yellow stuff here. I wrote here, that seems hard to do. The reason why it seems hard to do is that in the segment problem I had before, I had a one list per slab, right? That trick I can't use anymore because these irritating rectangles, they cannot be put in one slab. They span slabs, right? So instead I use a trick that we also use a lot in IO-efficient algorithms, which I, many years ago, called multi-slabs. So a multi-slab is just a continuous range of slabs. Okay? So if I have some slabs here, then I have one multi-slab that starts here and ends here. I have another one that starts here and ends here. I have one that starts here and ends here. And I also have one that starts here and ends here. I have lots of them. How many do I have? Well, I have the square of the number of slabs, right? Approximately. That's why I actually decrease the distribution factor to root m over b, such that I have m over b slabs. That means that I now have room for a block in memory from each of these multi-slabs. And now let me show you the algorithm. Here it is. I do exactly like I did before. I sweep down. When I meet the top part of a rectangle that spans slabs, I put it in the multi-slab it fits in, maximum multi-slabs that it spans. When I meet the bottom, I do nothing. Also, when I meet a segment, a rectangle, I go to the relevant multi-slabs, look at all the segments in there. Either I remove them or report an intersection, exactly like before. In fact, the algorithm is exactly the same. The only difference is the fan out is smaller, and I'm having multi-slabs instead of slabs. Otherwise, it's the exact same algorithm. So the analysis is the same, so I get the exact same result. Yeah? Actually, yeah, I could use either queues or stacks. It doesn't matter. Yeah. I'm not removing something from the middle. That's the key, right? So when I come, either I put things in. We agree on that, right? And if I put it in that end or that end, doesn't matter from the algorithm's point of view. And the other time when I visit it, I actually always go through the whole thing. And for each thing, I either output it again or I delete it. So it's going to be a sequential scan, right? So it's going to end up. I just write it back to a list, right? So I need an output block to put it in. So I push it on another stack. Good. Good. So basically, it's the same algorithm I just showed you twice here. And so here's the homework. I want you to give me an algorithm that solves the problems that says up there. I can draw it easier for you. You should find the area of the yellow stuff. So you're given a bunch of rectangles. You should find the yellow area. So the output is a number. There's a hint. The hint is to first solve a completely different problem. Namely, solve them the problem of, for each y-coordinate you have here, so for each top and bottom, you compute, here's a y-coordinate, for instance, it's the top of this thing here. You compute the size of the intersection between this line and the rectangle. So you compute the yellow stuff. It's a number. So for each y-coordinate, you compute a number. Once you have those numbers, you can easily solve the original problem. This problem you solve this using distribution sweeping with the merge step. It's not as difficult as it sounds. And it's the only homework I'm going to ask you. Okay? And they're lying up here for those of you who haven't gotten them yet. So that was basically what I wanted to say today. I'm still going to say something then. This was just a teaser. So, but I told you about sorting, sorting lower bounds, cache oblivious sorting, and then this distribution sweeping, which was also like sorting, right? It's distribution just with this combined bit of sweep. And then on Monday, I'm going to continue and tell you more data structure type stuff. Here's, if you want to go and read, here's basically 3 papers that will give you everything I said, not necessarily in the way I said it, but still it'll give it to you. This was the original paper that sort of defined this whole area. This is the paper that introduced distribution sweeping, and this was the paper that introduced the cache oblivious model. There's other places you can read some of the stuff that I went over, especially if you go to my homepage and go to my class, you can find some class notes and stuff that will also explain this. But I thought I would give you the right references. And we'll put the slides online also in a minute. All right, now comes the advertisement. So I hope you wondered what this Center for Massive Data Algorithmics is that I say that I'm center director for. So I wanted to tell you that. So it's a center by the Danish National Research Foundation. What happened was that 20 years ago, the Danish government decided to sell all the pension funds of all government employees. Since a huge fraction of the Danish population are government employees, this was a very, very big pension fund. and they got a lot of money for it. And they put all that money in a foundation that support basic research centers, where they basically give people like me up to 10 years of money to do whatever they want. So this was why I came home from the US. I left my job at Duke University to come back and lead one of these centers, because you get a lot of money for 10 years, you can do whatever you want. And here's what we want to do. This is the punchlines when we tell the foundation what we want to do. We want to do good research, basic research. We want to try to talk to other researchers in other fields, which we've heard a lot about today. It's important in these massive data areas, about solving their problems. And then we also want to see if we can push it out into industry. But here's what we really do. We do IO-efficient algorithms that I'm talking about. We do cache-oblivious algorithms that you just heard about. We do streaming algorithms that you will hear about, I think. And then we do algorithm engineering, actually going out and implementing them. So it's all algorithms in this kind of area where we look at big data set. And we try to do that very good by building on a strong team and a lot of international collaboration. So this team is in Aarhus, but actually we have sub-teams at MIT. So Piotr Indyk and Eric Demain is part of the center. And at the Max Planck Institute and Frankfurt University in Germany, where Kurt Mehlhorn and Ule Meyer is part of the center also. So we have collected all these strong people, and then we visit each other a lot. We have a lot of visitors, and this is where you come in. We have a lot of visitors coming all the time. We have yearly summer schools. We have a lot of activity going on. This was one of our retreats where we met up. Here's the interesting thing. Oh, it's red, you can't see it. We are hiring. All right, we're hiring on all levels. We hire postdocs, 2 to 4 postdocs a year. We have lots of PhD positions. I think we're 20 PhD students right now and 8 or 9 postdocs. And we continuously have openings. Well, every semester we have openings for postdocs and PhD students. So take a look at Madalgo. Search for Madalgo and look at it and see if that's something you're interested in. And we have a lot of fun. So that was what I want to say. Questions? Yeah. To which one? Mm-hmm. Yeah. Actually, if you look in that paper I was referring to here, no, it's a good question. This paper here actually does the same as what I just did. It goes through a couple of examples, and then it lists a huge number of problems that you can solve with the same techniques. And then there's been a couple of follow-up papers, including one by me, where you show that you can also use the technique in higher dimensions by decreasing fan-out and stuff. So the answer to your question, the answer to your exact question is yes, you can solve that problem. And the further answer is you can solve all kinds of problems that involve axis parallel stuff. If things are not axis parallel, things get really complicated. For instance, if you want to solve the general line segment intersection problem, it's much harder. There's a paper on that also, but it's not optimal. I can try, right? So it's always hard to explain why something is not possible. Well, because I don't know if it's not possible, I just haven't been able to solve it. But I think I would say that we tried a lot to solve the general intersection problem. That's really one of the big open problems. And I think the main reason that's hard is that when things are orthogonal, you can sort of, what I used all the time here was to put one segment in one slab, whereas when it's tilting, you don't know what order things come in, and things can come in different order, and right, the y-coordinate of one thing can be above a y-coordinate of another and intersect or not, you don't know. So things get a lot more complicated in those areas. But there's lots of interesting literature to read. Yeah.
My question is
That's good.
the material part mostly applies to
Mhm.
And you were interested about flash storage in terms of
Yes, yes.
efficiency, or you may just refer it as a very small
No, no, no. There's a bunch of paper. Actually, Uli Meyer at Frankfurt and his group has done a lot of stuff on IO efficient algorithms on flash storage. Most of it has actually been experimental, where they tried to look at using IO efficient algorithms on flash storage, and also tried to experimentally look at the various different architectures that actually are inside these, because they're actually not the same. You think that they're the same, right? But what's really going on in there is that you do have blocks access, but read and write are different, and there's also things can get old and all this stuff. So there's all kinds of complicated issues. But the take-home message is, yes, you can use IO-efficient algorithms on flash storage, and it'll be good also. In fact, Uli and his group, by using those techniques and also some other stuff, they have, I don't know if they've been beaten by now, but at least last year, they took home the world record in sorting by using these kind of ideas and building their own Perl machine with flash storage. Other questions?